Hello everyone. So, in physics, a lot of people sometimes make you assume things without showing you derivations or proper examples that allow you to fully understand a concept. And one of these things that happened to me was the relationship between wave velocity through a medium and the tension on the medium, for example, a wire. So today I'm going to show you just how to do that and what the relationship is and how to derive it. Okay, so let's get started. So first of all, we have to assume a certain function for our wave. And this wave is going to be moving across the wire. So it has to be time dependent. And here is a simple example of a wave. So you have y, which is a function of x and t, is equal to a sine times 2 pi over lambda parentheses x minus vt. So now let me take you through what everything in this is. This is the height of the wave above the wire's rest position. So it essentially means if you're going to graph this, it's the height above the x-axis. Its variables are x and t, and it's time dependent, just like we said. A is the amplitude. So a traditional sine function would have an amplitude of 1, depending on what your units are. But A will change that. It'll make it get higher or lower. Lambda is the wavelength. And on a wave, the wavelength is the distance between the two crests of the wave. So it's essentially a measure of how long, the length that it takes for a single, almost like you call it, beat of the wave to go by. The velocity is the velocity of the wave, which is v here, and t is time. And if you've had some experience in algebra and mathematics, you'll know that when you subtract something from the x term of an equation, it shifts the entire thing to the positive x direction, which is why this wave, since we're subtracting vt, moves to the right, not to the left, like someone might assume. So, let's keep this here. And now let's get on with the actual derivation. So first what we're going to have to do is find an equation which is called the wave equation. And this relates the rate of change of slope on the wire to the acceleration of the wire. Now, forewarning, you have to know some calculus for this. So just well, there's probably a lot of calculus videos out there, and basically all you have to know is derivatives and second derivatives, and that's all. Okay, so let's get started. Let's imagine we have a little piece of wire. Okay? And one end of this wire is at position, let's call it x, and the other is at position x plus delta x. So we know that the length of this wire is delta x. Now let's look at the tensions on this wire. Let's call this tension T1, and let's call this tension T2. Now we know that the rest position of this wire falls along this axis, right there. So what we can do is we can label these angles right here, and let's label them alpha for T1 and beta for T2. Okay? Alright. So, what we can now do is, if we assume that this piece of wire is not moving along this axis, since on a wave we have a transverse wave. So that means that the pieces of the medium only move up and down and not in the direction of the wave. And if we assume this is how our wave works, then this piece of wire cannot move along this axis, which means that the net force must be 0. So what we can write is that T1 cosine alpha, which is the horizontal component of the tension 1, must equal T2 cosine beta. But we can also say that that is also equal to the actual measured tension of the wire. Okay? Alright. So now what we can do is, we keep moving. We know from Newton's second law that the sum of the forces acting on an object must equal its mass multiplied by its acceleration. So what we can say is, the only part of this wire that's going to be moving is in the y direction. It's going to be moving in the y direction. So the y components of t2 and t1 are the only things that are going to make this accelerate. So, since they're in opposite directions, when we add them up, we actually have to subtract them. Since they're moving in opposite directions, vectors cancel out that way. So anyway, t1 sine alpha minus t2 sine beta must equal m times a, but we're going to write this a certain way. M we can also write as the linear density, which we'll call rho, multiplied by delta x. That's m. And remember, delta x is the length. So the linear density is mass per unit length. This is the length. This is mass. And we can write acceleration as the second derivative of y with respect to time. And if you know that velocity is rate of change of position, and acceleration is rate of change of velocity, then you know that acceleration is the rate of change of the rate of change of position. And so that's where we get this. Now, we can relate these two equations. But we have to do it one certain way. So, let's get to it. If we divide this equation by this equation up here, what we can get is, well, we're not changing the equation at all. Since all of these are the same, we're not changing the equation. It's still true. Except we can strategically put these inside the other equation so that we can simplify dramatically. So here's what we're going to do. We're going to divide t1 sine alpha by t1 cosine alpha. Then we're going to subtract the next term, which is t2 sine beta. And as you might have guessed, t2 cosine beta. And this is going to equal, we're going to divide the next part by t. So this is going to be equal to rho over t delta x second derivative of y with respect to t. Okay? Alright. So now what we can do is this. We can simplify this dramatically, as I said before. The t1s cancel for here. The t2s cancel for here. And just remember, this is still true because we've divided this entire equation by the same number everywhere. This is the same as this, and this is the same as this, and this is the same as that. They're all the same. So it's like dividing the whole equation by 2. Everything's still equal. So now, we know that sine over cosine of one angle is the tangent of that angle. So now we have tangent alpha minus tangent beta equals rho over t delta x second derivative with respect to time. However, let's move to the side here for a second. Let's consider a triangle, or just a line on the Cartesian coordinates system. This is a line y equals mx plus b. Yeah? Okay. So, here's what we can say. This is theta. This has a slope m. Ugh. Anyway, it has a slope m, and this is delta y, rise, and this is delta x, run. Rise over run is m. So we can write that. M equals delta y over delta x. However, this can also be written as some number multiplied by sine of theta. Because sine of theta in this case would be if this was length 1. But we know that it's not necessarily. So we just multiply by a coefficient and it's equal. And this is equal to the same number times cosine of theta. Now if we find the tangent of these, tangent of theta is sine over cosine. But remember, delta y is a sine theta, delta x is a cosine theta. If we replace delta y and delta x with those corresponding values, the a's will cancel out, and you'll have sine over cosine or tangent. So we just do that. We prove that the slope of any line or any segment or line of line-like object is equal to the tangent of the angle that it's at to the horizontal. And from basic calculus, you'll know that the slope can also be written as the change of y with respect to x. And that's not just for lines, but for any function. If you choose a point, this will be the instantaneous slope on it. Okay. So what can we do with our equation here? Well, here's what we do. Let's put that up there. We can rewrite tangent of alpha as the partial derivative of y with respect to x sub 1. Let's just put a subscript of 1 on y and x, because alpha is on this side of the wire. So and the slope here is obviously going to be different from the slope here. So we'll just label this with a subscript of 1. And correspondingly for beta, we'll label it with a subscript of 2. Okay, so here's what we have after that. The partial derivative of y1 with respect to x1 minus the partial derivative of y2 with respect to x2 equals this. But I'm going to rewrite it. Let's bring delta x over to this side. So we divide both sides by delta x. And what we can do is this. Delta x. And this is going to equal rho over t, second derivative of y with respect to t. Now, let's do something to this wire. If you take in a bit of calculus, you'll know that as we shrink this piece of wire infinitely small, we'll get to a point at which these two tensions become approximately equal. But also, delta x will be 0. So if we actually calculate this out, we get 0 over 0, and that just doesn't make sense. So what we have to do is take the limit. And when we take the limit, what happens is this is the difference in the slope of the wire over delta x. And what we can call this, and this is completely analogous to the definition of a derivative. It is the rate of change of a value with respect to its variable. And so this is if we take this limit as delta x goes to 0, this is the derivative of the derivative. And so therefore we get the second derivative of y with respect to x. And from this, what we've essentially done is proven what is called the wave equation. That the second partial derivative of y with respect to x is equal to rho over t, partial derivative of y, with a second partial derivative of y with respect to t. And this is an extremely important equation. It shows up everywhere. It shows up anytime you use a wave of the form y equals a sine 2 pi over lambda x minus vt, which is the standard model of a moving wave. And so this shows up even in quantum mechanics for Schrodinger's equation, which describes how particles can move and interact as waves. And so this is extremely, extremely profound. And we just calculated it using a page and a half, which is great. Okay, this is the hard part. It's over now, okay? So don't you worry about anything anymore. All we have to do now is take this equation and solve it for this equation. So let's actually do that now. Okay, so we know that y is a sine theta 2 pi over lambda x minus vt. And if we take the derivative of that, the derivative of y with respect to x is, well, what are the coefficients on x? Because the chain rule says we take the derivative of the entire thing and multiply by the derivative of which is on the variable. If you have multiple functions which are intertwined with each other. Composed. There we go. Composed. If you have a composed function inside of another function, you multiply the derivatives of both. So what do we have here? X has the coefficient 2 pi over lambda. And we know that if we take a derivative of a sine function, we get a cosine function. So here's what we do. The partial derivative is 2 pi over lambda multiplied by a cosine 2 pi over lambda x minus vt. Okay? If we take the second derivative, we take the derivative of this. And if we try taking the derivative of this, what are the coefficients on x, first of all? Well, it's the same thing, 2 pi over lambda. So essentially what we do is we take the 2 pi over lambda and bring it out again, and we multiply by this. So the second derivative of y with respect to x, and sorry, this might be a little slanted because of that, because it's hard to move your hand. But anyway, it's going to be 4 pi squared over lambda squared. But now, the derivative of cosine, of any cosine function, you replace the cosine with a negative sign. So let's put the negative over here. But wait a minute. If this becomes sine again, a sine 2 pi over lambda x minus vt, that's our original function. So just to save paper and time, I'm just going to write that as y of xt. So we now know that the second derivative of y with respect to x is negative 4 pi squared over lambda squared multiplied by the original function. Okay, that's great. So now what we're going to do is this. Bring this over here. Okay. Now we're going to take the derivative with respect to time. So the first derivative, let's kind of separate those. The first derivative with respect to time is going to be, well, what are the coefficients on time in this equation? Well, we have 2 pi over lambda multiplied by negative v. So we have to bring those outside. And we follow the same pattern we did before. 2 pi over lambda. And I have negative v, so let's put the negative out here. Negative 2 pi over lambda v times a cosine 2 pi over lambda x minus vt. So now we take the derivative of the derivative, or the second derivative. And what we have to do again is bring out negative 2 pi over lambda v. But remember, the derivative of any cosine function goes back to negative sign. So let's think about the negatives first of all. We have a negative 2 pi over lambda v. We multiply it by another negative 2 pi over lambda v. So that gives us positive 4 pi squared over lambda squared, v squared. But since cosine is going to a sine, we have to put the negative out there. So anyway, let's kind of write this out. So negative sign, the negative goes outside. We have 4 pi squared over lambda squared v squared. And then we have the original function again. We have a sine 2 pi over lambda x minus vt. So let's just write y times x, y of xt. Okay, now we have our two second derivatives. Now what we have to do is plug them back into the original equation. So let's do that down here. So we have second derivative of y with respect to t, of x, sorry, equals rho over t second partial of y with respect to t this time. So now let's solve that and plug in these values we have up here. Okay. So, what what we can do is this. Let's plug those in. Negative 4 pi squared over lambda squared y equals, let's put that there, equals negative 4 pi squared over lambda squared v squared y. These terms cancel. The y cancels. Oh, sorry about this. I forgot to put the rho t out here from this equation. So, sorry about that. The rho t was always there. This is because you have to plug that into the equation. So the rho t is there. So what we essentially get at the end of this is 1 equals rho over t v squared. And now we've just simplified this tremendously. So now we're going to solve for v. Ugh. Okay. So now when we solve for v from the original equation, 1 equals rho t v squared, we invert rho over t. Autofocus. Oh my gosh. Okay, anyway. Rho over t, we invert it and bring it over to the other side. So now we have t over rho equals v squared. And finally, we square root both sides. And we get v is the square root of t over rho. This is the relationship between wave speed and tension of the medium, preferably when it's a wire. So, when I was taught this in my class, we were just told that it depends on the medium at which it travels through. The speed of the wave depends on the medium. And it clearly shows that. The only variables here depend on the wire, which is the tension of the wire and the density of the wire. So, now you know that if v is related to the square root of t, and you know it for a reason. Alright guys, thanks so much for watching. Like it if you liked it, and have a great day. See ya.